Welcome back. In this video, which is our final in this health stats series, we'll talk about the chi-square test for goodness of fit. So the chi-square test for goodness of fit is very similar to the chi-square test for association, which we talked about in the previous video. However, what this goodness of fit test does is check whether or not a single categorical variable matches up with some hypothesized distribution. So in general, our test statistic looks very similar. Our null and alternative hypothesis in this test are very similar as well. We're just simply focusing on the distribution of a single categorical variable. How is this one variable distributed? Does it match a model that we're thinking of, or does it not? So again, there are some rules of thumb that we'll need to check, and software will luckily do this for us. They're both based on the sample size. So the rules of thumb that R checks is that the categories all have an expected frequency greater than 1, and that no more of them have expected frequency less than 5, or no more than 20% of them have this small of an expected frequency. Most of the time, you will be warned if the sample size assumption or if these two sample size conditions are violated. So do be aware of that possibly creeping into your output. If you get a warning, that indicates that your sample size might be too small to use this procedure. So let's illustrate how this goodness of fit test works with some examples. So melanoma is a fairly rare form of skin cancer that accounts for the vast majority of skin cancer fatalities. One cause of melanoma is increased UV exposure. So the more sun or UV light exposure you have, the more likely it is that you might develop melanoma. Now, some parts of the body are more regularly exposed to the sun than others. So, for example, in the summer, you might go out in a tank top and shorts, which means that your arms, your legs, might be more exposed to the sun. So, a random sample of 310 women diagnosed with melanoma were classified according to the known location of the melanoma on their bodies. So, 45 women had melanoma on their head or neck, 80 women had it on their trunk, so their midsection, 34 on their upper limbs, so their arms, 151 on their lower limbs, their legs and feet. So we will assume that these body parts represent roughly equal skin areas, which might be a dubious assumption. We could also think about it as they represent roughly equal exposure. So for example, my face is typically uncovered throughout the year, so that would receive sun exposure even in the winter, whereas I typically don't wear shorts in the winter. My legs would receive less exposure over time. So here's our thought. Do the data support the hypothesis that melanoma occurs evenly on the body, so is equally likely to occur on these 4 regions? So our null hypothesis is that the melanoma occurs according to this distribution, so occurs equally likely on all 4 regions. Our alternative is that it's not. Now in this bar chart here, what I've gone ahead and done is added boxes that represent that null hypothesis. So these empty boxes represent the model that we'd like to compare to. Looking at our data, some of these boxes are underfilled, some of these boxes are overfilled. We're seeing a lot more incidence of melanoma in the lower limbs, so the legs, a lot less in the head and neck and upper limbs than we would expect to see if it were evenly distributed or evenly dispersed in these 4 areas. So our null hypothesis, again, is that melanoma occurs evenly on the body. Our alternative is that it does not. In order to do this chi-square test, we need to create 2 lists or 2 vectors in R. One will contain our observed counts. So here are the observed counts, just writing the values from the table. We had 45, 80, 34, and 151. The expected should contain the expected proportions, not the expected counts. So if they're evenly likely, we would expect 25% of cancers to occur on the head and neck, 25% on the trunk, 25% on the arms, 25% on the legs. So that's where the expected proportions are coming from. To do our chi-square test, we'll use the chi-square.test function. X is our observed values, P is our expected proportions. Here we have a very small p-value, so pretty compelling evidence that melanoma occurrence is not evenly distributed on the body. Now let's take a look at another example. So the FDA has recently requested that every effort be made to include individuals of all major ethnic backgrounds when enrolling subjects in clinical trials. So recruiting a diverse subject pool for clinical trials can definitely be a challenge. Recruiting a large enough pool is a challenge in and of itself. But this guidance suggests that more needs to be done to ensure that our samples are representative. As evidence for this, they referred to an article that was published in the New England Journal of Medicine. This described how effective calcium and vitamin D supplements were in preventing hip and other fractures in postmenopausal women. Now, what we're looking at here isn't the effectiveness of these supplements, but actually the distribution of how the subject pool was chosen. So here we have the sample of women. We have the number who were enrolled in the study according to the major ethnic backgrounds in the U.S. The categories that were used in this particular study were white, Black, Hispanic, Asian Pacific Islander, and Native American. This second row here, percent in the U.S., represents the percent of the U.S. population at the time the study was completed. So at the time the study was completed, 75.6% of women in the U.S. were white, 10.8% of women in the U.S. identified as Black, 9.1% identified as Hispanic, 3.8% identified as Asian Pacific, 0.7% identified as Native American. So here is the question. Do the proportions enrolled in the study match with the background in the U.S. at the time? So again, here is a bar plot with those proportions drawn on in empty boxes. So if the null hypothesis is satisfied and if this is a reasonable model, we would expect the boxes to all be roughly filled in. Here we see some over-representation. We certainly have more white representation in this study than we did in the population at the time. We have fewer Asian Pacific Islanders, fewer Black subjects, fewer Hispanic. Native American looks about right with the proportion of the U.S. population at the time. Certainly we have a lot of underrepresentation in the other categories. So our null hypothesis is that the study matched the ethnic diversity in the U.S. at the time it was taken. The alternative is that it did not. Again, we will enter our observed and expected proportions into R. The order here does not matter as long as it is consistent. So as long as the first element in the observed list is the same as the first element in the expected list, that's what we're going for. Typically, I'll just go in the order that's specified in the table. So looking at our chi-squared test, we have a p-value that is, again, very, very small. So we do have strong evidence that this study did not match the ethnic diversity in the U.S. at the time. If you've made it all the way through this series of videos, thanks for watching and hope to catch you again soon. Bye.